Hello everyone. Now we will see a video on resonance circuit and then we will see an example as well. Okay. So there is a very rare chance that they will ask question from resonance in interview, but in written test there will be one or two question from resonance. So that's why it is important to study this concept. Okay. So I will just tell the concept that is useful for you. Okay. Not quality factor and everything I won't discuss here. Okay. So for that you can watch complete lectures, complete some gate series or anything like that. You can watch, but whatever is needed for the placements that I will tell here. Okay. Yeah. So first for series RLC, this is a simple series RLC circuit. Okay. And this is one voltage source connected here, and this is the current. So this will have some frequency component. This will also have some frequency component. Okay. So V can be written as V equals to I into Z impedance. V is the voltage applied. V j omega. We will shortly write it as V, voltage applied. IR equals to IC equals to IL equals to I of j omega, because the complete current is flowing through R, L and C, so all of them will be having the same current flowing. Okay. And Z is the total impedance. So I into Z. This is looking like IZ, so it would be I into Z. So V equals to I into what is Z? Z is R plus J omega L minus 1 by omega C. I will write here. What is the impedance provided by the resistance? It is R. What is the impedance provided by the inductance? It is J omega L. And what is the impedance provided by the capacitance? It is 1 by J omega C, right? So this will be the total impedance. So your Z is R plus J omega L minus J 1 by J omega C. And and whatever the circuit you have, if you are asked to calculate the resonance frequency, you find the expression of impedance or admittance. You just need to find the expression for impedance or admittance, and at resonance frequency you just put the imaginary part equals to 0. Okay. You just find the expression for impedance or admittance, anything, impedance or admittance, and just put the imaginary part equals to 0. So putting the imaginary part equals to 0 at resonance, omega R minus 1 by omega R C equals to 0. So your omega R will be, that is your resonance frequency. It will be equals to 1 by root LC. So this is your resonance frequency. Okay. At resonance frequency, what is happening here is that your magnitude of Z is equals to magnitude of Z minimum. Here I should also write the magnitude of Z. What is the magnitude of Z? Root R square plus omega L minus 1 by omega C square. So this factor goes to 0. So the magnitude of Z is equals to Z minimum, that is equals to R. That means your impedance is minimum. Okay, impedance is minimum. So drawing the plot here, your impedance is minimum. So this is mode of Z and this is frequency. Okay. So at this point, omega equals to omega naught, we have minimum impedance, that is equals to R. Here frequency is lesser, right? In this area we have less frequency, so omega L will be less and 1 by omega C will be more. For omega less than omega naught, omega L will be lesser than 1 by omega C, right? Because this is less value, so it will be more, right? So this will be capacitive and this area will be inductive, right? And now if your Z is equals to Z minimum, then your current mod of I is equals to I maximum, that is equals to V by R. What was your current? Your current was V by this impedance. If this is minimum, the current will be maximum. So at resonance, your current will be maximum. So now drawing the plot. So at resonance, omega equals to omega naught. This will be I maximum, that is equals to V by R. Okay. Now what you see, like this is the maximum frequency, right? Now there will be some point, let us call this one as omega L and this one as omega H. So there will be some point where you have a 3 dB lesser frequency, sorry, a 3 dB lesser amplitude of current. What is 3 dB frequency? What is 3 dB frequency? Frequency at which the current I is I max by root 2. It means the current in dB is I max in dB minus 3 dB. If you calculate this in dB, 1 by root 2, if you convert it in dB, it will be 3 dB. So at 3 dB frequency, you have a current equals, your current will be equals to I max by root 2. So it will be equals to V by root 2 R. Okay. So at 3 dB frequency, what are the 3 dB frequency? Omega HL, omega L. Okay. So at 3 dB frequency, your current is the root 2 times of maximum current. Okay. Now finding 3 dB frequencies. Now you need to find 3 dB frequencies. So it is a simple derivation. Okay. What is current I? Current I is equals to V by root R square plus omega L minus 1 by omega C square at omega equals to omega 3 dB. Okay. So at 3 dB frequency, I equals to I max by root 2. That means V by root 2 R. So V by root 2 R is equals to V upon root R square plus omega 3 dB L minus 1 by omega 3 dB C whole square. So omega 3 dB L minus 1 by omega 3 dB C equals to plus minus R. So this is the equation you have. By solving this will you get 2R square minus R square. So this is what you get. So at omega 3 dB equals to omega L. Okay, at this frequency. At lower frequency, omega L will be lesser, right? At lower frequency, this will be less, and this will be like, right, I should write here. At omega 3 dB equals to omega L into L will be lesser than omega L into C, right? That means this value equals to minus R. This value is less, this value is more. So this will be equals to minus R. So omega L into L minus 1 by omega L into C equals to minus R. And omega H into L minus 1 by omega H into C equals to plus R. Right? So by solving now, what do you get? your omega h is equals to r by L plus root r by L whole square plus 4 by LC by 2. This is omega h. Okay, and what will be omega L? Omega L will be minus r by L plus root r by L whole square plus 4 by LC by 2. Okay, now there is one term 3 dB bandwidth. This is very important. 3 dB bandwidth. This is very important. So this 3 dB bandwidth omega 3 dB bandwidth omega h we should write omega 3 dB bandwidth omega not h, we can't write omega h. For omega 3 dB bandwidth we are writing omega naught, not omega naught, we should also not write omega naught, we can write. Okay, so it will be omega h minus omega L. So this value minus this value, it will be equals to r by L. So that you should remember. In series RLC circuit, what is 3 dB frequency? Sorry, what is 3 dB bandwidth? It is r by L. Okay, and what is resonance frequency? It is 1 by root LC. Okay, and there is one more relation between resonance frequency and lower cutoff frequency and higher cutoff frequency. This is higher 3 dB cutoff frequency, higher 3 dB cutoff frequency, and this is lower 3 dB frequency, lower 3 dB frequency. Okay, so there is a relation between resonance frequency and higher and lower cutoff frequency, that is equals to this. The resonance frequency is the geometric mean of higher cutoff frequency and lower 3 dB cutoff frequency. Geometric mean. Geometric mean of higher cutoff frequency and lower cutoff frequency. So that's it. That's the whole analysis. So this you should remember. The resonance frequency you should also remember, and you should also remember the curve with respect to frequency. This is the curve with respect to frequency. So depending on the value of frequency, this is the curve we get. Okay, at 1 by root LC we will get the maximum current. Okay, and the curve of impedance you should also remember. Okay, so this is the complete analysis for series RLC circuit. Now we will see the analysis of parallel RLC circuit. Okay, now coming to parallel RLC circuit in the next video. So now coming to the parallel RLC circuit, we are seeing the resonance concept of resonance here, and now coming to parallel RLC circuit. So here what you can write, here you can write I equals to V by R plus V by j omega L plus V into j omega C, right? Nodal analysis we are applying. Okay, basic KCL equation. So your I by V will be equals to 1 by R plus 1 by j omega L, 1 by j omega L plus j omega C. And what is I by V? That is equals to Y. Like what is V equals to I into Z, right? So Z is equals to V by I. This is what we call impedance. Okay, and what is admittance? Admittance is the reciprocal of this, that is admittance. Okay, so you can simply write I equals to V into Y, V into Y, that you can write. Okay, so that is admittance. So what is the magnitude of admittance? That is equals to 1 by R plus root, before writing the magnitude we should write the exponential, we should write this complex form. It will be equals to 1 by R plus j omega C minus 1 by omega L, right? This j will go above, so it will be minus 1 by R plus j omega L minus omega C minus 1 by omega L. So what will be the magnitude of Y now? It will be 1 by R square plus omega L minus, sorry, omega C minus 1 by omega L whole square under root. And what is the one thing I have told you? At resonance I told you, in any circuit, if you are asked to find the value of resonance frequency, what you will do, you will find the expression for admittance or impedance and will just put the imaginary value equals to 0. So here we are finding the expression of admittance, and now we will just put the imaginary value equals to 0. So that will be equals to omega R will be equals to 1 by root LC. So this is the resonance frequency, that is equals to 1 by root LC, that is resonance frequency. Okay. Yeah. So at resonance, what happens is that this value will be 0, right? So your y will be equals to, at y minimum, that will be equals to 1 by R. That means minimum admittance and maximum impedance. Your what is I? I is equals to V into Y, that I told you, right? So your V will be I by Y. Your V will be I by Y, right? So your voltage will be maximum, right? At resonance, your admittance will be minimum and your voltage will be maximum. Drawing the curve of admittance, let me elaborate it. So your VR is equals to VL is equals to VC equals to V minimum. Here you can see, here your VR is equals to VL equals to VC equals to minimum value of this. Sorry, maximum. Sorry, maximum. V maximum. Okay. So drawing the curve of admittance, at resonance frequency it will be minimum. So it will go like this. At omega equals to omega naught, it is equals to 1 by R. Okay. So at lower frequency, here we have lower frequency. Okay. Here we have lower frequency. At lower frequency, this will be more. 1 by omega L will be more. Right. So at lower frequency, this is inductive and this is capacitive. At lower frequency, 1 by omega L will be more. So inductive effect is more, and after that capacitive effect will be more. Okay. And drawing the curve of voltage, where did I write Y? Yeah. Okay. This is omega equals to omega resonance. So this is V max, that is equals to I into R, right? Because your Y is equals to 1 by R. So your V will be equals to I into R, right? And there will be one 3 dB frequency. I don't need to rewrite the concept of 3 dB frequency now. So here we will have the value equals to V max by root 3. So this is omega L, this will be omega H. So here we will have the magnitude equals to IR by root 3. So again, your V is equals to I upon root, your V is equals to I by Y. V is equals to I by Y. And what is the value of Y? Value of y is 1 by r square plus omega c minus 1 by omega r. Okay, this can seem a little bit different from the series RLC analysis because we are not habitual of writing the admittance value, but you just go by the concept, then it will be easy. So this is the value we are writing, right? Okay, so at omega equals to omega 3 dB, V is equals to V max by root 3. So it will be IR by root 3 equals to I upon root 1 by R square plus omega C minus 1 by omega L whole square. So from here you will have omega H, that is equals to 1 by 2 RC plus 1 by 2 RC whole square plus 1 by LC, and your omega L will be equals to minus 1 by 2 RC plus root 1 by 2 RC whole square plus 1 by LC. Okay, so your 3 dB bandwidth, so for 3 dB bandwidth, so this is very important formula. So your 3 dB bandwidth will be omega naught, it will be 1 by RC, right? And there will be one more relation between resonance frequency and upper and lower cutoff frequency, that is equals to this. Okay, so this is the complete analysis, right? So first we saw that your voltage will be maximum here, and then we calculated the 3 dB bandwidth, that is equals to 1 by RC here, and in this case it was equals to R by L. Okay, so how you can remember? So in series RLC it is like the RL circuit, and what is the time constant of RL circuit? It is L by R. So frequency will be just opposite, it is R by L. Okay, you understand it? So it is R by L. What is the unit? Radian by second. Here also you will have radian by second unit. Okay, so and in series RC, what is the time constant? RC, right? So just the opposite, just the reciprocal, so it would be 1 by RC. So these things you should know about the resonance circuit in series and parallel RLC. Okay, first the resonance frequency, then the 3 dB bandwidth, and then this relation. Okay, so that's it. Now we will see one question. Okay, thank you. Hello everyone, now we will see the examples. So here you need to find the 3 dB bandwidth for the given circuit. Okay, so this is parallel RLC circuit. Okay, so what is the 3 dB bandwidth? 3 dB bandwidth, we were presenting it with omega naught, it was equals to 1 by RC, but here the R is 2R, 2R, 4R, 4R and 4R, 2R, right? R equivalent C we can write, so it is equals to 2R, 2R, 4R, 4R, 2R, so it is equals to 1 by 2RC, so it will be equals to 2 into 1 into 1, so it will be equals to 0.5 radian per second. Okay, so this was a simple question, just you need to see the value of resistance here. Okay, so it was 2R, so this is the value of 3 dB bandwidth. Now seeing this question, this is a very good question. Here you have a IST as a square waveform, okay, of amplitude 1 ampere. So this is the input you have, okay, and then you have a parallel RLC circuit. Now at what frequency, at what frequency you will have the highest magnitude of V0T? What will be the approximate frequency of the component of highest amplitude seen at V0T? So at what frequency you will have the highest magnitude? At resonance frequency, right? So what is resonance frequency? Omega R equals to 1 by root LC, right? So 1 by root LC, 10 to the power, oh, this we need to modify. This is 1 picofarad, okay? This is 1 picofarad. So it would be 1 upon 10 to the power minus 12 into 10 to the power minus 6. So it would be 10 to the power 9. So it would be around 1000 mega radian per second. So what is the nearing value? This one. But this is wrong. This is wrong. Why so? Because this concept is valid if your current is, here you can see, if you have applied a voltage source, you could have applied a current source here as well. Okay. Now, there is a mistake in this concept. This should have been a current source only. This should have been a current source only. Here. This should be a current source, I of j omega. Okay. And then we will have some V voltage. So for all the frequency component, you had the same current. If there is 5 ampere current flowing here, so the current 5 ampere will be same for all the frequency component. At frequency component 1 radian it is 5 ampere, at 1000 radian it is 5 ampere, at 5000 radian it is 5 ampere only. The current will be always 5 radian. The current will always be 5 ampere. Okay, so the current will be same for all the frequency component. But here this is what? Square wave, right? This is square wave. What are the frequency component it will have? DC, omega naught, 3 omega naught, 5 omega naught, and so on. And also I told you to remember the magnitude. So what is the magnitude? Magnitude is 2a by n pi. So here it will be 2a is 1 ampere by n pi. Okay. So for omega naught it will be 2 by pi. For 3 omega naught it will be 2 by 3 pi. For 5 omega naught it will be 2 by 5 pi. What is the value of omega naught? 333 mega radian per second, right? What is the value of 3 omega naught? 999 mega radian per second. Okay. Now what did you see? The amplitude, the voltage amplitude, like at omega equals to around 999 mega radian per second, or you can say 1000 mega radian per second, or 1000 mega radian per second. What did you see is that omega L is equals to 1 by omega C. Okay, that means your V naught will be I into R, that you saw, right? Okay, but the thing is that the magnitude of I is 1 by 3 times lesser than the magnitude of I at omega equals to 333 mega radian per second. At 333 mega radian per second, the magnitude of I at 333 mega radian per second, the magnitude of I is 2 by pi ampere. Okay, and at 999 mega radian per second, your magnitude of I is 2 by 3 pi ampere. So the magnitude of I s at 999 mega radian is 1 by 3 times of magnitude of I at 333 mega radian. Do you understand this? The magnitude is 1 by 3 times. Okay. So now what you need to do is you need to calculate the V naught T in both of the cases. For 999 mega radian per second, for 999 mega radian per sec, your omega L is equals to omega C. So your circuit will reduce to something like this. Right, and here you have current 2 by 3 pi, and this is your V naught. So your V naught will be 2 by 3 pi into R. So R is 1, so it will be 2 by 3 pi volts. So that's the answer we are getting. Your V naught is 2 by 3 pi volts. And now at 4333 mega radian per second. Okay, your circuit will be something like this. What will be the value of current? 2 by pi, right? Now for all the frequency component, the current is not same. Okay, the analysis that we did, the graph that we draw, something like this, that was for the condition that the current for all the frequency components are same. But here the current is not same for all the frequency component. the current is changing 2 by 3 pi, 2 by pi. So at 333 megaradian, you will have the component R in action. You will also have L in action, right? You will also have C in action, right? All the frequency components you will have, and 2 by R current will be flowing, and this is V naught. Okay, so this is L and this is C. So what you can write is that V naught by R plus V naught by j omega L plus V naught into j omega C is equals to 2 by pi, right? So V naught by R is 1, V naught by j omega is, what is omega here? 333 mega. And what is L? L is 1 micro and C is 1 pico. L is 1 micro and C is 1 picofarad and this is 1 Henry. So 1 micro and 333 mega. So it would be 333 mega into micro 1, right? Plus V naught J 1 micro into this. So it would be 333 micro, right? Equals to 2 by pi. So V naught equals to 1 plus J 333 micro minus 1 by 333. Okay, that will be equals to 2 by pi. So it would be V naught into under root of this value 1 plus 333 micro minus 1 by root 333 whole square equals to 2 by pi. Now if you solve this, you will get to know that this value is almost equals to 1. Shouldn't write in this manner. This value will almost be equals to 1. So here your V naught is coming out to be 2 by pi volt. So what do you see here? Your V naught at 333 mega radian per second is 2 by pi volt, while your V naught at 2 by 3 while your V naught at 999 mega radian per second is 2 by 3 pi volts. What happens here is that at 333 mega radian frequency, these components are getting cancelled, almost getting cancelled. Okay, so these components are almost getting cancelled at what frequency? At 333 mega radian frequency as well. So at 333 mega radian frequency, you have this V naught, while at 999 mega radian frequency you had this V naught. So which is larger? So your V naught at 333 mega radian per second is larger than your V naught at 999 mega radian per second. Okay, so this is the case, and at omega equals to 0 radian per second, what happen? Omega L will be 0. So this will be your circuit. At omega equals to 0, you have 1 by 2. This is R. Your L will be shorted and your capacitor will be open circuited. Right? This will be the condition. Right? So what will be V naught? It will be 0 volts only. Okay. So what should be the answer? The answer would be 333 mega radian. So this is the correct answer. Okay. Did you understand the complete problem? What happens here is that we did this analysis where the current was same for all the frequency component. The current was same for all the frequency component. But here in this square wave input, the current is not same for all the frequency component. The current is getting reduced with increased frequency component. So the current is getting reduced. And so I was saying that the current is getting reduced. Okay. So because the current is getting reduced, we have to check at what frequency what is happening. Okay. So now I will give you an intuitive approach here. So we are given that your R is 1 ohm, your L was 1 micro Henry, and your C was 1 picofarad, and this was parallel RLC, right? Parallel RLC. Okay. So what was the resonance frequency omega r 1 by root LC, so it was around 1000 mega radian per second. And what was the 3 dB bandwidth omega naught, omega h minus omega l, that was equals to 1 by RC. Okay, so that will be equals to 10 to the power 6 mega radian per second. So if we draw the frequency response for this circuit, what we can see, like this is the point of V naught max that is occurring at 1000 mega radian. Okay, and from here if you go to 3 dB, this is the 3 dB bandwidth, right? This point and this point, this will give you the 3 dB bandwidth, right? So this area and this area would be same. So if this complete, like let us take this as x, this as y. So x plus y is your 10 to the power 6 mega radian per second, and your x is equals to y. So your x will be 10 to the power 6 by 2 mega radian per sec. So it would be, so this value, this is 10 to the power 6 mega radian per second already. No, this is 10 to the power 9 mega radian per second, right? Like no, this is the value, this value is 10 to the power 3 mega radian per second, right? And now this value is 10 to the power 6, 10 to the power 6 by 2. So this value will be some negative, like your omega L would be 10 to the power 3 minus 10 to the power 6 by 2 mega radian per sec. Okay, and your omega H would be 10 to the power 3 plus 10 to the power 6 by 2 mega radian per sec. So it will be highly negative, right? And this will be highly positive. So your voltage component is getting reduced by V naught max by root 2. So it is getting reduced by 1 by root 2 factor. Getting reduced by 1 by root 2 factor at omega equals to 10 to the power 3 minus 10 to the power 6 by 2 mega radian per sec. Like at very low frequency, at very low frequency, your amplitude is reduced by 1 by root 2 factor. Okay, at very low frequency. So at 333 mega radian per second, means at 10 to the power 6 mega, at 10 to the power 3 mega radian per second, at 10 to the power 3 mega radian per second, you have V naught max value. So where will be 333 mega radian per second? At here only, because this point is highly negative. Okay, so 333 mega radian will come here only, right? 0 mega radian will come somewhat here, then these 3 mega radian, just assume like 3 radian will come here, 0 radian will come here, then more values will come, like this is highly negative. So this 3 mega radian will be nearly close to this, right? So your V naught max will simply be same. For what? For the same value of IS. It will be nearly equals to at r mega radian per second V naught value. Your V naught value for 33 mega radian per second and your V naught value for 999 mega radian per second, it will be nearly same, right? Your V naught value will be nearly same for same value of IS, same value of IS, but IS of 333 megaradian per second is 3 times of IS of 999 megaradian per second. So what you can see here is that your V naught is getting reduced by a very little margin, but your IS is getting increased by a very large margin for 333 megaradian per second. Do you understand this concept? If you don't understand this concept, simply go by this analysis, simply by finding the values. But just try to think once. This is the curve for, just listen once carefully. This is the curve for same current. If the current was same, in the whole circuit the current was same, then the value of V naught T at 999 megaradian per second would be nearly equals to the value at 333 megaradian per second. The V naught value at 999 megaradian per second and V naught value at 333 megaradian per second would be the same if the current flowing in the circuit was same. But what do we see here is that the current in 333 megaradian per second is 3 times larger than the current in 999 megaradian per second. So here it is reduced by negligible margin, but the current is getting increased by 3 times margin. And what is V naught? The V naught is IS into impedance. So this is getting increased by 3 times margin, but the impedance is not getting decreased by much margin. So impedance is almost the same. So this value will be increased by, so your V naught at 333 megaradian will be 3 times of your V naught at 999 megaradian per sec. That's why your answer will be 333 megaradian. If I have shown this voltage waveform here, you could have simply drawn the waveform of Z. Like the waveform of Z would be the same, right? If the waveform of Y is something like that, this then waveform of Z will be the same. So your Z is not getting decreased much. Your Z is not getting decreased much, but your Z is not getting decreased much, but here your I is getting increased by 3 times. That's why your voltage will be larger at 333 megaradian per second. Okay, so I hope you have understood this question. Okay, so this was a very good question. Okay, thank you.